My name is Dr. Ken Bogen from the San Francisco Bay Area. I work for a consulting company called Exponent with offices throughout the U.S. and the world. I spent 20 years at Lawrence Livermore National Laboratory as a University of California employee, environmental scientist, and served on the National Research Council committee that wrote Science and Judgment in Risk Assessment back in 1994. My talk today, well, it was yesterday, at the Dose Response 2010 conference, focused on a generic hockey stick modeling approach to estimating benchmark dose and potency for toxicity data, in particular as an alternative to the US EPA's benchmark dose software procedure, which is widely used throughout the United States and the world, as a way to characterize toxicity from experimental toxicity data.
Can you hold that thought one for 1 second?
Sure.
I'd like to get a little closer shot of you, and that looks better. Okay, and you can continue.
This US EPA approach that's commonly used now by state regulatory agencies and organizations with responsibilities to comply with environmental regulations uses a suite of models that serve to as a basis for predicting and modeling the dose-response relationship observed in any particular set of toxicity data. And a question arises, is this complicated procedure of using many different models that comes along with a complicated decision tree in order to help the user evaluate the output that's generated by this complex approach. Is this procedure worthwhile? Is it flawed? How does it perform relative to the much simpler single generic hockey stick model that I propose as an alternative? When you're modeling toxicity data, you really only have a limited set of animal dose response data that you work with by and large. And my impression is that applying this multi-model decision tree approach is overkill and is not justified by the amount of information in a limited data set. So what I did was compare my simple approach to the EPA approach and show that my approach performs as well, if not better, from a statistical point of view, using data simulated from all the different models that are considered by the EPA procedure. Basically what I showed is that the EPA procedure misspecifies which actual model was used to generate each set of simulated data that I used, so that the information you're getting from this more complicated approach is illusory and misleading. Statistically, it also performs either worse or only just as well as this much simpler procedure. Another interesting aspect of the new approach that I applied is that it takes an objective approach to determining whether or not there is an initially negative dose response. The EPA procedure, the way it's used commonly, basically presumes that there is never an initial negative dose response or hormetic dose response. So the models are restricted, by and large, to those that presume what we call a monotonically increasing response per unit dose at low doses. So my approach is more objective and can characterize a negative as well as a zero or positive dose response. And I finally illustrated this capability by applying my approach to assess the carcinogenic potency of a chemical called anthraquinone. The chemical is interesting insofar as it is the basis for a series of anti-tumor agents used chemotherapeutically in humans to treat leukemia. Well, it turns out that this compound, anthraquinone, essentially cures male and female rats of leukemia as well, and quite dramatically so. But it also increases kidney tumors in rats and increases liver tumors in male and female mice. So this chemical carcinogen, which also occurs in the environment, poses an interesting question as to how a regulatory agency should best set low concentration safety standards for the presence of this chemical in various media, such as water and products that come in contact with food, etc. Right now, the regulatory process only considers whether a chemical increases the risk of cancer, and those are the only data considered. But here's a case where exposure to the chemical clearly can do both, increase as well as suppress the risk of cancer. And in order to figure out how not to increase public health risk, you need to consider both possibilities and to do so quantitatively. And my model offers a way of doing that. Thank you.